Hello everyone, today we're going to do another conceptual plan. Now we have the situation as weak acid and strong base titration. Okay, so in saying that, I'm going to draw my picture again. Okay, so now you have your burette, okay, and you have an Erlenmeyer flask. Again, in this case, you will have your weak acid in the Erlenmeyer flask, and then you have your strong base here. In this case, just say I'm going to use sodium hydroxide, okay? And then again, we're going to have 4 different stages of this titration, okay? So the first one will be the initial, okay? So initial, what do you have? Like I said, we didn't release any base into the solution yet, so you only have weak acid in your solution, okay? And then how do you calculate the pH of a weak acid? Yes, we talked about this has been a while, right? Okay, so how do you do it? You need to set up your S table, solve for X, okay? You solve for X, and then this X will be the concentration of hydronium ion, and then you can do your pH equals to negative log of this hydronium ion, okay? So that's how you do initial, okay? And then as when you start, okay? So that will be, we will call as before equivalence point, okay? So before equivalence point, okay? So now I'm gonna start to add this base, okay? So I'm adding some, okay? Add some of this base, okay? So you're gonna add small amount. Again, this sodium hydroxide. So we recognize we're gonna have a reaction, okay? So the sodium hydroxide will react with our weak acid. I'm gonna use HA because we didn't specify what it is, okay? And after the reaction, you're gonna have NaA, okay? And H2O, okay? So you're gonna have this two, okay? So as we said, you only add small amount, so this sodium hydroxide will be your limiting reagent. That means it's gonna run out. So it's gonna run out. So it's gonna run out first, okay? So whatever this amount you added, excuse me, and then since it's a 1:1:1 ratio, you're gonna use the appropriate amount, the same amount actually of the acid to neutralize it, and then you're gonna create or produce the same moles of the salt. Okay, so just say we're gonna have then you're gonna create the same moles. Okay, so that means after this neutralization reaction, this will be running out, and then you have HA. Okay, and you also have the salt you produced from this process. Okay, these two put together, you go, this is a weak acid, as we said, okay, and this is what is sodium. Against not, it's a cation for strong base, so it's not gonna affect the pH. So that actually the A minus, right, that anion will affect your pH, and this is what actually is the conjugate base of the weak acid. Okay, so now what do you have? Weak acid and conjugate base, you put together these two, yep, we have a buffer solution. Okay, so you have a buffer solution. Okay, so for this buffer solution, of course, you have to calculate the concentration. You have to calculate the concentration of these two. Okay, these two. After the first step, you calculate the concentration of both. Then you can calculate the pH of this buffer. Will be pK, Heisenberg equation, very convenient. Then you can use the base over the acid concentration. Remember, this two is the new concentration. It's not what the question provided. You have to do a stoichiometric calculation here. Then you'll be able to find out what's the concentration of each. Okay, so I'll just give you some number over here. Okay, just say you added we'll say 0.1 mole. Okay, you added 0.1 mole. Okay, so that's initial, and then just say you had 1.2 moles of the acid, okay, and then you're gonna consume this 0.1 moles of the base, again as your limiting reagent, and then you go, what's my left over? what's my leftover moles? That's 1.1 leftover moles, and then I have 0.1 leftover moles of the of that salt. Okay, and then of course you know the volume, you can divide by the volume. Like I said, since they're in the same condition, in the same solution, actually the ratio of the concentration will equal to the ratio of the moles. Okay, so you can just use whatever this x you added. Okay, so this now you can just give assumption. Just say this the base will assume it's x. Okay, original acid will say is y. Okay, so then if you try to plug it in, that will be what? The moles at the end will be the y minus the x you added. That limited to 1 to 1 to 1 ratio, right? So that will be this. Okay, and then the moles of the salt you produce gonna be x, right? Okay, so that's what you have, and then the salt is your base. If you try to plug that in, this will be what? The pKa plus log of the base will be this x, whatever you're adding. Okay, so the x minus the acid will be y minus x. Okay, so then you do this, and then that should give you the pH value. Of course, pK you have to go for the K, doing like a log of the K, then you can calculate the pH at this moment. Okay, excuse me. So that's what you do. Okay, and then let's keep on moving. Okay, so at equivalence point. Okay, at equivalence point. So we already know the moles of the hydrogen ion equals to the moles of hydroxide ion. So what does that mean? One more time, in your setup. Okay, so I'm gonna copy mine in your setup. Okay, over here. So you're dividing. Okay, so eventually you add enough of this base. Okay, enough of base. Okay, so acid base completely neutralize each other. So both of them are out. Okay, as we said, similar to the strong situation. So you're gonna have this equation. So you're gonna have HA. Okay, then you're gonna have NaA and H2O. Okay, so both of them gonna be gone because again they are at equilibrium. They completely react with each other, no acid base left. Okay, so then that means you will have only what? You're only having this salt and water at equivalence point. Okay, and then this salt is not pH neutral. It's gonna be what? It's gonna be weakly basic. Okay, so it's going to be weakly basic due to what? This is a conjugate base of a weak acid. Okay, so and then you're just going to deal with the calculation when you have the anion, the conjugate base of a weak acid, react with water, and then you're going to have HA and OH. Okay, so it's going to be weakly basic. Of course, you can set up your S table and continue the calculation. Okay, so over here, now make sure you calculate the concentration of this salt. Okay, just say now you added, both of them are going to be x, right, because they just completely react with each other, and then at this moment you have 0 of this, but you have x moles of this salt produced. Okay, and then before you go ahead to your S table, make sure you turn this moles into concentration. This will be what? Or equals to the moles, wherever the moles you're adding the moles over the total volume at this moment will be the volume of the acid HA plus the volume of the base you added. Okay, so that's gonna be the concentration, and then now you can set up your S table, and then if you're given with K, you turn it into KB, then you set up your S table. Okay, so then you're gonna go ahead with your S table and then solve for the X. Okay, in this case, this X will equals the concentration of hydrogen ion, then you know how to get to the pH. Okay, so that's how we do at equivalence point. Okay, and then after equivalence point, things are the same situation as a strong, because after, okay, so after equivalence point, all the acid is gone, right? So I'm gonna do this one more time. Okay, so again, thinking about in your elemental flask. Now what do you have? Okay, so now you are this acid is all gone. Okay, acid is all gone because you kept adding more of the base. Okay, so what's gonna happen? You're gonna have some leftover base, whatever you used to neutralize the acid, whatever leftover base, and then this conjugate base of acid, and this is so weak. So after equivalence point, you can actually just ignore it. Okay, so then you just calculate the pH of leftover NaOH. Like I said, this is the same process as how you did it for the strong. So what do? You're gonna use the moles of NaOH minus the moles of the weak acid you had, and then divided by the total volume. So what will be the volume of the acid plus the volume of, up to this moment, the volume of the NaOH. Then you get the concentration of the OH, and then you know how to go to pH. Okay, so this is how you do when you have a weak acid and strong base. Again, it's similar to strong, but you have to realize you have a weak, you have to set as table to do the initial step. And before equivalence point is not, you have to do the stoichiometry calculation, then you have a buffer, then you're going to use Henderson-Hasselbalch equation, and then at equivalence point, the salt you have is not neutral, so pH doesn't equal to 7. pH in this case actually is going to be what? pH will be bigger than 7 because you have a weakly basic solution. So you're going to do this, set up S table, solve for the salt, okay? And then after equivalence point is the same as your have strong because this, the conjugate base of the weak acid is weak compared to a strong base. So you can ignore it, just calculate the regular way, and then you'll be able to get the pH at the end. Okay, so this is the conceptual plan for when you have a weak acid and strong base. No matter what, remember the first step, you can calculate the moles of the acid, moles of the base. You compare these two, then you will be figure out if it's at before, after, or at, and then you can just go for at that range what you need to do. Okay, so that's it for